The morning shift at the Haskell and Sons textile mill began like any other. Men shuffled through the factory doors at dawn, their breath visible in the cold air of March 1907. The new conveyor system, pride of management, terror of the floor workers, hummed its usual metallic song. Leather belts slapping against iron drums, the rhythmic clank of chain drives, steam hissing through pipes overhead. Then at 6:47 a.m., something changed. The sound shifted, a grinding noise, low and guttural, like something massive straining against itself. Workers looked up from their stations. The conveyor belt, loaded with spools of finished thread moving toward the packaging station, began to slow. Not a gradual deceleration, a stuttering, jerking motion, as if the machine itself was choking. Thomas Brennan, a 42-year-old line supervisor, felt it first in his boots. A vibration traveling up through the floorboards. Wrong frequency, wrong rhythm. He turned toward the main drive shaft just as the belt stopped completely. For 3 seconds, silence, pure industrial silence. No worker moved, every eye fixed on that motionless belt. Then it lurched backward. Not slowly, not cautiously, at full operational speed, but in reverse. Boxes of thread spools that had been moving east suddenly accelerated west. A metal toolbox sitting on the belt shot backward like it had been yanked by invisible rope. Workers shouted, scrambled. A young apprentice dove out of the way as a wooden crate careened past him, splinters flying where it clipped a support beam. The belt screamed. That's the word every witness used later. Screamed. The friction of leather against iron drums, spinning the wrong direction, created a sound like something alive and suffering. Black smoke rose from the drive pulley. The smell of burning rubber and hot metal filled the air. Brennan ran toward the main cut-off lever, boots pounding the floor. But before he could reach it, the belt stopped again. This time for nearly 10 seconds. Workers stood frozen, watching. Then, as suddenly as it had reversed, the conveyor lurched forward again. Normal direction, normal speed, as if nothing had happened. The only evidence was the scattered cargo, the burnt smell, and the 37 men who had just watched a machine decide, entirely on its own, to run backwards. Management blamed operator error. The workers knew better. They had just witnessed something that shouldn't be possible, something that defied every principle of how a conveyor system was supposed to work. And it was only the beginning. 6 weeks earlier, the Haskell and Sons mill had installed what they called the future of industrial efficiency, a mechanical conveyor system designed by the Parsons Engineering Company of Philadelphia, 28 feet long, powered by a 12-horsepower steam engine driving a series of leather belts, iron pulleys, and geared shafts. On paper, it was magnificent. In practice, it was assembled by men who had never installed such a system before, working from incomplete blueprints, under pressure to finish before the spring production push. The main belt, 10 inches wide, 3/4 of an inch thick, was mounted on 6 roller drums. The drive pulley sat at the western end, connected to the steam engine through a reduction gear assembly. Tension was maintained by a single adjustable idler wheel. The entire system was designed to move at a constant 4 feet per second. But from the first day of operation, something felt wrong. Michael Kowalski, a machinist with 17 years of factory experience, noticed it immediately. He placed his palm against the main support frame during the initial test run. Felt like a heartbeat, he said later, but irregular, like the machine was struggling. The vibration wasn't constant. It pulsed. Every few seconds, a spike in intensity that traveled through the frame, rattled the mounting bolts, and made the belt flutter slightly. Kowalski reported it to his foreman. His foreman reported it to management. Management consulted the installation crew. Normal break-in period, they were told. Give it 2 weeks. But 2 weeks passed, and the vibration didn't smooth out. It got worse, more erratic. Workers began to recognize patterns. The belt would tighten and loosen seemingly at random. Sometimes it ran beautifully for hours. Other times it would slip on the drive pulley, creating a horrible squealing sound and leaving black friction marks on the metal. The tension system was the first obvious problem. The idler wheel, meant to keep constant pressure on the belt, was mounted on a sliding bracket with a single spring for adjustment. But the spring tension was set for a brand new belt. As the leather stretched and settled over the first few weeks, the system couldn't compensate. The belt developed slack. Not much, maybe half an inch of play. But in a system moving thousands of pounds of cargo daily, half an inch was catastrophic. Then there were the pulleys themselves. 6 identical drums, supposedly. But when Kowalski measured them one night after his shift, he found variations. The third drum was 3/16 of an inch smaller in diameter than the others. Tiny difference. But it meant that drum completed more rotations per minute than its neighbors. The belt was being pulled at different speeds simultaneously. Workers started calling it the temperamental beast. Some refused to load heavy cargo near the drive end. Others claimed they could predict when it would act up based on the sound. A certain pitch in the motor meant trouble was coming. A particular rattle in the overhead shaft meant the belt was about to slip. Management dismissed these concerns as superstition. Workers were being irrational. The machine was fine. Production numbers were up. But everyone on the floor knew the truth. They were working alongside something unstable, something that obeyed its own rules. And when it finally decided to reverse direction that March morning, not a single worker was surprised. They'd been waiting for it. In the days following the first reversal, strange symptoms multiplied. The belt began to flutter, not constantly, but in episodes. Workers would watch the leather surface ripple like water, waves traveling from the drive pulley toward the far end. The ripples moved opposite to the belt's direction of travel. One machinist described it as watching a snake move backward while its body went forward. Tools started migrating. A wrench placed on the stationary platform beside the conveyor would somehow end up 15 feet upstream by day's end. A oil can left near the third roller appeared at the first. Workers joked about it, the ghost shift moving things around. But underneath, the humor was genuine unease. Objects don't move themselves. The pulleys developed personalities. The second drum, workers swore, rotated smoothly for exactly 43 minutes before developing a wobble that lasted 6 minutes, then corrected itself. Like clockwork. The fifth drum occasionally rotated backward, just a quarter turn, maybe less, before catching up to the correct direction. You could see it if you watched carefully. A brief reversal, a stutter, then compliance. Stoppages became unpredictable. The system would run flawlessly for days, then stop and start 17 times in an hour. No pattern, no warning, just sudden deceleration, pause, and resumption. During these episodes, the steam engine continued running at normal speed. The problem wasn't power. Something in the mechanical chain between engine and belt was deciding when to transmit force and when to hold back. The sounds changed too. Workers learned to interpret the acoustic landscape of the machine. A high-pitched whine from the drive shaft meant the belt was about to slip. A deep grinding noise meant one of the bearings was dry. A clicking sound, irregular, like a clock with broken teeth, meant trouble nobody could identify or fix. By April, the factory floor had split into factions. Some workers believed the machine was fundamentally flawed and should be dismantled. Others thought it just needed proper adjustment. A third group, smaller but vocal, whispered about deliberate sabotage. Maybe a disgruntled worker was sneaking in at night, loosening bolts, applying grease to create slippage. The foremen didn't know what to believe. They filed reports describing mechanical anomalies and intermittent operational irregularities. Management responded with orders to keep production moving. The machine was expensive. Shutting it down for inspection would cost thousands in lost output. Whatever was wrong, the workers would figure out how to work around it. Then came the rumors. Someone claimed the conveyor reversed direction every time the factory whistle blew at shift change. Not true, but the story spread. Another worker insisted the machine only misbehaved when the steam pressure dropped below a certain threshold. Also false. A third theory involved the lunar cycle, the full moon somehow affecting the belt tension. The truth was simpler and more terrifying. Nobody understood what was happening, not the workers who operated it daily, not the foremen who managed production, not the engineers who had designed and installed it. The conveyor system had become a black box. Input, steam, power, and human labor. Output, unpredictable mechanical behavior and growing fear. And everyone knew the first reversal wouldn't be the last. The backwards conveyor wasn't cursed. It was doomed by physics. Start with the flywheels. The steam engine driving the system used two massive cast iron wheels, each weighing 300 pounds, to smooth out the pulses of the reciprocating pistons. These wheels stored rotational energy, enormous amounts of it. At full speed, they contained enough kinetic energy to run the entire factory for 30 seconds, even if the steam supply was cut. This was intentional. Flywheels prevent stalling. But the Parsons system used two flywheels operating asynchronously, one connected directly to the engine crankshaft, another positioned between the reduction gears and the main drive shaft. They weren't synchronized. They couldn't be, given the gear ratios involved. So they rotated at different speeds, storing and releasing energy on different cycles. Most of the time, this worked. But occasionally, the timing aligned in catastrophic ways. The primary flywheel would slow down while the secondary was still at peak velocity. For a fraction of a second, the secondary wheel was trying to drive the system faster than the engine was providing power. The result: the system would jerk forward, overloading the belt, creating slack. Now add the belt itself. Leather, not chain or cable. Leather stretches. As it heated up during operation, from friction, from the steam-warmed factory air, it expanded. Not uniformly. The section running over the drive pulley got hotter than the section hanging free between rollers. So the belt developed uneven tension. Tight spots and loose spots traveling around the circuit like waves. When a loose section hit the drive pulley, it would slip, briefly lose contact. During that slip, the pulley was spinning but not transmitting force to the belt. The belt would decelerate, but the flywheels were still spinning. They stored that energy, waiting. Then the belt would catch again, suddenly re-engage with the pulley. But here's the critical part. Because of the slack that had developed, the belt was slightly out of phase with the pulley rotation. The pulley had advanced ahead of where the belt expected it to be. The belt did what any flexible material does when pulled from an unexpected angle. It tried to equalize tension by moving in the opposite direction. Just for a moment. Just enough to take up the slack. But in a system already destabilized by asynchronous flywheels and thermal expansion, that moment was enough. The reverse torque propagated through the system. The secondary flywheel, still holding its massive rotational energy, suddenly found itself fighting against the belt's motion instead of supporting it. It acted like a brake, but a brake that was also a motor. It absorbed the forward momentum and converted it into backward force. Meanwhile, the shaft alignment made everything worse. The main drive shaft between the engine and the first pulley wasn't perfectly straight. It deviated from true by maybe 3 degrees, barely noticeable during installation. But 3 degrees of misalignment meant the shaft was constantly flexing as it rotated. Flexing created oscillating stress. That stress transmitted through the bearings into the support frame, and from there into every component of the system. The shaft's flex changed the load on different parts of the belt at different moments. Sometimes the belt was being pulled mostly from the center, sometimes from the edges. This uneven loading caused the belt to track poorly on the rollers, drifting left, then right, never running true. Poor tracking meant uneven wear. Uneven wear meant unpredictable friction. Add thermal expansion of the metal components themselves. As the factory warmed up during the day, the iron pulley drums expanded. Not much, maybe a few thousandths of an inch, but enough to change their effective diameter. A larger diameter meant higher surface speed at the same rotational velocity. So as the day progressed, the pulleys were effectively trying to run the belt faster than the engine was designed to drive it. All these factors, asynchronous flywheels, belt slippage, thermal expansion, shaft misalignment, friction imbalances, existed in every belt drive system of the era. But in most systems, they averaged out. They damped each other. The Haskell conveyor was different. Through sheer terrible luck, these factors reinforced each other. They resonated. When conditions aligned, belt temperature between specific ranges, shaft flex at peak oscillation, both flywheels momentarily desynchronized. The system would cross a threshold. Forward motion would stall. The stored energy in the flywheels would reverse direction, and 37 workers would watch their conveyor belt run backwards at full speed. It wasn't supernatural. It was just engineering on a knife's edge. May 14th, 1907, third shift, 11:40 p.m. The factory ran on reduced crew during night operations, only 14 men to maintain the machinery and handle the smaller production loads. The conveyor had been behaving for 3 days straight. No slips, no strange sounds, no unexpected stops. Management was pleased. Maybe the system had finally settled in. Joseph Darrow, the night foreman, was doing paperwork in the glass-walled office overlooking the main floor when the temperature shifted. Not outside, inside. The factory suddenly got warmer. He looked up, confused. The steam lines were all operating normally. Then he realized the ventilation fans had stopped. Both of them. Someone would need to check the fan motor, but that could wait until morning. What Darrow didn't realize, the temperature increase would push the conveyor belt past a critical threshold. At 11:52, the belt began making a sound nobody had heard before. Not the usual hum or squeal, a deep, rhythmic thumping, like a massive heartbeat. Workers stopped what they were doing. One man put his hand on the support frame and immediately jerked back. "Jesus Christ, it's vibrating so hard it burned me," he said later. The thumping got faster, louder. The entire frame was shaking now, mounting bolts rattling in their holes. The belt developed a visible wave pattern, a standing oscillation moving up and down the length like something trying to escape its own skin. Then the main drive shaft screamed. Metal on metal, a horrible shrieking that made men clap their hands over their ears. The shaft was flexing so violently it was bending its own bearings. One of the flywheels suddenly decelerated. Workers heard the change in pitch, while the other kept spinning at full speed. The belt stopped moving, complete stop, but the steam engine was still running. Power was still being transmitted to the system. It had nowhere to go. The stored energy in the flywheels built up, compressed into that secondary wheel still spinning at maximum velocity. Darrow ran out of his office, screaming for everyone to get back. He knew. He couldn't say how, but he knew something catastrophic was about to happen. The belt didn't just reverse. It exploded into reverse. Full speed, maximum velocity, backward. Boxes that had been sitting stationary on the belt launched themselves toward the drive end like they'd been fired from a cannon. A metal toolbox hit the support frame so hard it punched a dent into the iron beam. Wooden crates shattered against the rollers, splinters flying. A coil of rope that had been resting on the platform got caught by the moving belt and whipped around, nearly taking off a worker's arm. The sound was apocalyptic. Leather belt moving backward against rollers that were still trying to spin forward created friction so intense the belt began smoking along its entire length. Black smoke, thick and acrid. The drive pulley was glowing red at the contact point. Workers saw it clearly, a cherry red line marking where the belt was being dragged against its will across metal heated past tolerance. Tools flew. A hammer sitting on the belt went airborne when it hit a roller, tumbled through the air, crashed through a window. A wrench caught in the drive mechanism and got chewed into pieces, metal fragments scattering across the floor. Men dove behind machinery, under workbenches, anywhere that offered protection from the debris. The shaft was screaming continuously now, a sound so loud it drowned out the steam engine itself. One of the mounting bolts sheared off completely, snapped like a twig, and the entire support frame shifted 6 inches to the left. The belt, still running backward at full speed, began to track off the rollers. It was trying to tear itself free of the system. Darrow finally reached the main cut-off valve. He grabbed the lever with both hands and hauled it down. Steam pressure dropped. The engine began to decelerate, but the flywheels were still spinning. They had so much stored energy that even without steam, they kept driving the system. For 40 seconds, witnesses timed it later, the conveyor continued running backward on pure momentum. Slower and slower, but still moving, still dangerous. Men stayed hidden until it finally shuddered to a complete stop. When they emerged, the factory floor looked like a battlefield. Shattered crates, scattered tools, burn marks on the floor where hot metal fragments had landed. The belt itself was destroyed along a 6-foot section, leather torn, stitching ripped, the material twisted and warped from heat damage. And the smell: burnt rubber, hot metal, wood smoke, and something else, something chemical and wrong. The smell of a machine that had been pushed past its breaking point. Nobody said the word cursed that night. They didn't need to. They had just survived something that shouldn't exist. A machine that could reverse itself, violently, with enough force to destroy whatever stood in its way. The conveyor belt didn't run. Nobody said the word cursed that night. They didn't need to. They had just survived something that shouldn't exist. A machine that could reverse itself, violently, with enough force to destroy whatever stood in its way. The conveyor belt didn't run again for 6 weeks. When it finally did, it was with an entirely different crew. The men from the night shift refused to work near it ever again. The damage was too severe to ignore. Management had no choice. On May 16th, they brought in a 3-man team from the Mechanical Engineering Society of Philadelphia. Real experts. Men who had designed and analyzed industrial systems across the country. Lead engineer was a 58-year-old named Edgar Whitmore. 2 decades of experience with belt drives, gear systems, steam power. He arrived at the Haskell factory with measuring instruments, notebooks, and a reputation for finding problems everyone else had missed. The first thing Whitmore did was stop everyone from cleaning up. He wanted to see the carnage exactly as it had been left. He walked the length of the conveyor system 3 times, not touching anything, just observing. Then he asked for every installation document, every blueprint, every modification log. The documents told the first part of the story. The system had been installed by a general contractor, not by Parsons Engineering directly. The contractor had made 17 unauthorized modifications to save time and money. Shaft diameter reduced, cheaper bearings substituted, pulley spacing altered by 3 inches to fit the existing floor anchors. Whitmore started with the bearings. He had them dismounted one by one. 3 of the 12 main bearings were damaged, not failed, damaged, microfractures in the race surfaces, wear patterns showing they had been overloaded repeatedly. 1 bearing had so much play it could wobble nearly a 1/4 inch in its housing. Then the shaft alignment. Whitmore stretched a string line from the steam engine to the far end pulley. The main drive shaft deviated from that line by 2 3/4 inches, not degrees, inches. Over a distance of 30 feet, the shaft was bending its way through space like a slow-motion sine wave. He measured each pulley drum. The 3rd drum, the one Kowalski had measured months earlier, was actually ground incorrectly at the factory. It was supposed to have a slight crown, a curve that kept the belt centered. Instead, it was concave, dished inward. Any belt running over that pulley would naturally drift to the edges, creating uneven loading and premature wear. The belt itself was educational. Whitmore examined the damaged section under magnification. The leather showed signs of catastrophic heat damage, but also something else: grain separation. The belt had been assembled from 3 layers of leather stitched and glued together, but the glue had failed in several spots. The layers were delaminating. During normal operation, this created internal slippage, the outer layer moving at a slightly different speed than the inner layer. The belt was fighting itself. Most damning was the tension system. Whitmore removed the idler wheel assembly completely and brought it to his makeshift workshop. The spring that was supposed to maintain constant tension was the wrong specification. Too soft. It compressed completely under the belt's operating load, meaning it provided 0 dynamic adjustment. The belt could slacken and tighten at will, and the tension system would just passively follow along. But Whitmore's critical discovery came when he analyzed the flywheel system. He had both wheels removed from their shafts and measured their rotational inertia. The secondary flywheel, the one between the gears and the drive shaft, had 3 times the rotational mass it needed. Someone had specified the wrong wheel. It was meant for a larger industrial system. That excess mass meant the secondary wheel stored far more energy than the system was designed to handle. And because it was operating through a reduction gear assembly, it was spinning faster than the primary flywheel. Much faster. At full operation, the secondary wheel was rotating at 240 revolutions per minute, while the primary was doing 80. Whitmore did the math. Under certain conditions, belt slippage, thermal expansion, shaft flex all combining, the secondary flywheel could briefly decouple from the forward load. For maybe 2 seconds, it would be spinning free, no resistance. When the belt caught again, that wheel would discharge its energy backward through the system. He calculated the forces involved. The secondary flywheel at full speed contained enough energy to reverse the entire conveyor system, belt, pulleys, cargo, everything, and accelerate it backward to approximately 60% of normal operating speed in less than 3 seconds. It wasn't a machine that occasionally failed. It was a machine designed to fail. The only mystery was why it didn't reverse direction every single day. Whitmore wrote a 60-page report. Management read 15 pages before stopping. The conveyor system would need to be completely dismantled and rebuilt. New shaft, new bearings, new pulleys, new belt, new tension system, different flywheel, better alignment, professional installation. Estimated cost, more than the original installation. They did it anyway. They had no choice. But the report itself disappeared into a file cabinet, marked confidential. The public would never know how close they came to industrial disaster, and the workers who had survived it would never receive an apology. The Haskell and Sons conveyor disaster should have become a textbook case. Engineering schools should have studied it. Trade journals should have published warnings. Factory inspectors should have used it as an example of what not to do. Instead, it vanished. No investigation by state authorities, no insurance inquiry, no public report. By August 1907, the story had died completely. Even the local newspapers, which had initially covered the mysterious conveyor malfunction, stopped mentioning it. Why? Start with liability. The Haskell factory was responsible for worker safety. The system's failures had nearly killed men. If the true cause, catastrophic design flaws, unauthorized modifications, inadequate oversight, became public knowledge, the company faced massive legal exposure. Workers could sue. Families could sue. The state could mandate expensive safety changes across all operations. So the company made a deal. With the workers, with the contractors, with everyone involved. Generous financial settlements, bonuses, improved working conditions, all in exchange for silence. The workers signed documents agreeing not to discuss the incident outside the factory. The contractors agreed to confidentiality clauses. Even the engineers from Philadelphia were paid extra to keep their report private. Then there was competition. Haskell and Sons operated in a cutthroat textile market. If competitors learned about such a catastrophic mechanical failure, they could use it for strategic advantage. Whisper campaigns, rumors about unreliable machinery, questions about product quality. In an era when reputation was everything, even a hint of major problems could destroy business relationships. Management decided the smartest move was to make it disappear. Fix the system quietly, move forward, never speak of it again. The workers, for their part, had their own reasons for silence. Many had families to support. Speaking out meant losing their jobs, maybe being blacklisted throughout the industry. In 1907, there were no worker protections, no unions strong enough to shield them from retaliation. If management wanted you gone, you were gone. Some workers did try to talk. Thomas Brennan, the supervisor who had witnessed the first reversal, wrote letters to 3 different mechanical engineering journals describing the failure. None were published. Michael Kowalski approached a reporter at the Philadelphia Inquirer. The story was killed before it went to print. Joseph Darrow, the night foreman who survived the big reversal, told anyone who would listen. By 1909, he was unemployed and couldn't find work in any factory within 50 miles. The physical evidence was destroyed. The damaged belt was burned. The fractured bearings were melted down. The misaligned shaft was cut apart and sold as scrap. The pulleys were remachined and installed in a different factory under different ownership. By 1910, nothing remained of the original conveyor system except Whitmore's confidential report, locked in a company safe. And the workers' memories. But memories die with the people who hold them. By the 1920s, most of the men who had witnessed the reversals were dead or had moved on. The younger workers who joined the factory later only heard vague rumors. A story about a machine that ran backwards, probably exaggerated, probably not even true. By 1950, the Haskell factory itself was gone, demolished to make room for commercial development. The company records were dispersed or destroyed. The few documents that survived ended up in historical archives, uncatalogued and unread. The backwards conveyor belt became a ghost story, an industrial legend, something old-timers mentioned but nobody quite believed. Until 1997, when a mechanical engineering PhD student named Sarah Chen was researching early 20th century industrial accidents for her dissertation. She found a reference to Whitmore's report in a footnote in an obscure trade journal. The footnote mentioned the Haskell factory. Chen spent 2 years tracking down surviving documents. She found Whitmore's report in the basement of a defunct insurance company, filed under miscellaneous industrial claims, denied. She found 3 worker testimonies that had been preserved in a separate legal dispute. She found installation documents in a contractor's archive that nobody had bothered to throw away. Chen's dissertation chapter on the Haskell conveyor became one of the most cited papers in mechanical failure analysis, not because the failure was unique, because it was typical. Most industrial disasters of that era were covered up, hidden, forgotten. The backwards conveyor was one of thousands that vanished into corporate secrecy and worker silence. History forgot, because history was never allowed to remember. Sometimes the machines of the industrial age didn't need ghosts or legends. Their danger came from flaws so small they could turn the entire system upside down. A bearing 3/16 of an inch too small, a flywheel specified for the wrong application, a shaft misaligned by 3 degrees, a spring that was 2 pounds too soft. None of these errors individually would destroy a system. But combined, compounded, allowed to resonate together, they created something that should have been impossible. The backwards conveyor wasn't an anomaly. It was a warning about what happens when complexity outpaces understanding, when cost-cutting compromises design, when workers' concerns are dismissed as superstition. The men who worked alongside that machine weren't irrational. They felt the wrong vibrations. They heard the dangerous sounds. They watched the belt flutter in ways that shouldn't happen. They knew something was catastrophically wrong weeks before the first reversal. But they had no power to stop it. No authority to demand changes. No voice that management would hear. And when it finally failed, when it reversed direction with enough violence to destroy itself, the response wasn't to learn from the failure. It was to hide it, bury it, pretend it never happened. That's the real lesson of the backwards conveyor, not the technical details of flywheel dynamics or belt tension. The lesson is about what we choose to remember and what we allow ourselves to forget. How many other disasters vanished the same way? How many workers were silenced? How many engineering reports were locked away to protect corporate liability? How many warnings went unheeded because acknowledging them would be expensive or embarrassing or inconvenient? The Industrial Revolution built the modern world, but it built it on a foundation of machinery that was barely understood, barely controlled, and far more dangerous than anyone wanted to admit. We remember the innovations, the breakthroughs, the brilliant designs that changed everything. We forget the conveyor belts that ran backwards, the boilers that exploded, The gears that failed. The workers who died or were maimed because someone cut a corner or used the wrong specification or ignored a problem that seemed small. The Haskell factory ran for another 40 years after the conveyor incident. Production continued. Profits were made. The new system, properly engineered, worked perfectly. And nobody who walked through those factory doors after 1910 had any idea that the floor beneath their feet had once been a battlefield. That's how industrial memory works. Success is documented. Failure is buried. And the distance between the two is often nothing more than a bearing that's slightly out of spec, spinning at 240 revolutions per minute, waiting for exactly the wrong moment to let everything fall apart. The conveyor belt that ran backwards taught us that machines don't need to be possessed to be dangerous. They just need to be misunderstood. And in the early 20th century, when mechanical systems were growing faster than human comprehension could follow, that misunderstanding was everywhere. We stand on the shoulders of giants, the saying goes, but we also stand on the wreckage of machines that failed in ways nobody anticipated. The difference is that we remember the giants. We've built monuments to them. We've written their names in textbooks and on plaques. The backwards conveyor, that's just a story, a weird industrial anecdote, a thing that probably didn't happen exactly the way people claim. Except it did happen, and it happened because of choices, human choices, about money and time and risk and whose voice mattered. The machine wasn't cursed, but the system that created it, installed it, operated it, and then covered up its failures. That system was broken in ways far more profound than any misaligned bearing could ever be. Sometimes the most dangerous thing in a factory isn't the machine. It's the silence about what the machine is actually doing, and why. The belt ran backwards because the forces aligned perfectly wrong, but it stayed hidden because the incentives aligned perfectly toward forgetting. That's the story, not just of one conveyor in one factory in 1907, but of an entire era when progress moved faster than understanding, and the cost was paid by people whose names we'll never know. The machine has been gone for over a century, but the pattern it represents, ignore the warnings, hide the failures, protect the bottom line, that pattern is still running, still pulling us along, still threatening to reverse direction when we least expect it. And we won't see it coming, we never do. Not until someone feels the wrong vibration through the floor, hears the dangerous sound that shouldn't be there, watches something move the wrong direction, and wonders if anyone will listen. This time,